This video is about the engineering challenge on page 3 of your homework packet. So your task is to design a system that maximizes the production of ammonia, which ultimately will be used in the production of fertilizer to spread across the great state of Iowa. Notice the oxymoron. Ammonia is produced according to the Haber process, which is nitrogen gas combines with hydrogen gas, forming NH3, and it is an exothermic. It releases energy. Now your job is to manipulate variables, temperature, pressure, concentration, and catalyst, and you're supposed to consider equilibrium and reaction rate. So if you want to produce NH3, you're going to want to shift equilibrium to the right. What can you do to temperature, pressure, concentration, and catalyst to shift equilibrium to the right? If you're trying to produce NH3, you're going to want to do it quickly as possible. So what factors can you shift here to make the product of NH3 more quickly? So consider those things, come up with your plan, and pause the video, and then come up with your plan. Okay, I think you might be back now, and we'll check your answers and see how you've done. I'm going to flip something over here and look at some possibilities. We'll see if we can keep this thing to stay up. I think we're doing pretty good here. Maybe I can get my papers here in a nice equilibrium or a balance here. Okay, so temperature-wise, equilibrium-wise, we are trying to shift this reaction to the right. So we're thinking of things we can do to shift the reaction to the right. If we think about temperature, the rule is shift away from what you add, shift toward what you take away. So if I add something to the right, it's going to shift left. If I lower the temperature, it will shift right. So in terms of equilibrium, I want to do this at a low temperature. For pressure, I want to shift things to the right. I count moles of gas. 1 plus 3 is 4 moles of gas on the left, 2 moles of gas on the right. If I do things at high pressure or increase the pressure, it's going to shift it to the right. So I want to do things at a high pressure to maximize my equilibrium concentration. If I increase this reactant, it's going to shift equilibrium to the right, or if I increase this reactant, it'll shift equilibrium to the right. So I want to have high concentrations of N2 and H2. NH3, that's what we're trying to make. Now, if I have a bunch of NH3 in the system, it's going to shift back. So as soon as I make the NH3, I'm going to pipe it away, probably put it under a cold temperature and high pressure to minimize that backward reaction. So if I keep pumping in the reactants and remove the product right away, put it under conditions where I can isolate that, like at a low temperature, I can keep driving this reaction to the right. And then a catalyst will have no effect on equilibrium concentrations. However, we will see that will affect rates. Now let's take a look at reaction rates. In order to produce this reaction at a faster rate to get NH3, I want to do this at a higher temperature. So we have a trade-off. If I do it at a real high temperature, I'm going to get it produced very quickly, which is advantageous, but I'll have a very low percent of NH3, which is not advantageous. So that would be a case where there's a trade-off. You'd have to look at the numbers, and that's what the engineers would do. Look more at our equilibrium constant expressions, and then figure an optimal temperature, which gives us a reasonable rate and a reasonable percent yield. As far as pressure is concerned, the higher the pressure, more collisions. It's like an increase in concentration of reactions. It will make this reaction faster. So pressure is like a win-win situation. The higher the pressure will make the equilibrium shift to the right, and it will also make it go faster. The trade-off would be the cost of a high-pressure system and also the safety concerns there. So as running a business, you're always going to be considering your costs. Let's see, N2 and H2. If you increase your reactants, that makes the reaction faster, and that also makes the reaction rate faster. So that's a win-win situation. You'd want to have those as high as possible. And then a catalyst, if you have an effective catalyst, it will speed up your reaction. There's no trade-off cost as far as equilibrium with a catalyst, so that's a win-draw situation. So adding an effective catalyst would be something that you would do. So these are some factors that you would consider, but again, if you're doing an engineering challenge, you're not only looking at equilibrium, we're also looking at rate, trying to maximize these productions. This was a very qualitative look, but at some point we won't do that, but you could look at numbers and then optimize those conditions, including cost and other factors. So complete that on page, or check over what you did on page 3 and complete that and let me know if you have questions.